Hello, this is the presentation of the final project of Computational Tools 1, in which the design and simulation of a centrifugal pump is performed. We are Kenia Yepes, Juan Felipe Dueñas, Cristina Lacotur, Ivan Lugo, and Stephanie Fraser. In this presentation, we have five relevant points: the introduction, the materials and methods, the results and analysis, the conclusions, and finally the reference. For the development of the project, it is necessary to understand what is a turbo machine and what are the characteristics of a centrifugal pump. A turbomachine is the equipment in which energy is transferred to or from a continuously flowing fluid. The transfer of energy is given by the dynamic action of one or more moving blades. In this sense, the centrifugal pump is a turbomachine that is characterized by converting the energy of the rotor into kinetic energy in a liquid by accelerating the fluid to the outer edge of an impeller. Another characteristic of a centrifugal pump is that the volume traps the liquid and slows it down, creating resistance. Finally, the centrifugal pump increases the pressure and velocity of the fluid.
The objective of this project is to design and simulate a centrifugal pump with the proposed geometries for the impeller and the volute that match the given specifications and determine the operational performance of the curve. To design our centrifugal pump, we used as a reference the design proposed by Valdez, which had a BEP of 250.1 cubic meters per hour, an efficiency of 78%, and a total head measurement of 93.41 meters.
The pump design includes three main components: the impeller, the housing, and the diffuser. The impeller, located inside the housing, is a rotating piece with blades that accelerate the fluid. The housing, the external structure of the pump, guides the flow of liquid to the impeller. After the impeller, the fluid passes to the diffuser, where its kinetic energy is converted in pressure energy before leaving the pump. It is important to say that the CAD model's internal volume was extracted using star CCM after it was generated with Autodesk Inventor.
In order to run the simulation in Star CCM, we need to run up the measures. The first one we run was with a base size of zero point 0.9 centimeter and a prism layer near wall thickness of 0.000423 centimeters. And the target size was the base size, and the minimum size was equal to 10%. After that, we run another mesh with a base size higher in a 30%, which means 1.17 centimeters. And finally, we run another mesh that was the fine one with a base size of 0.63 centimeters, which means 30% less than the base size the initial base size.
These model and conditions are essential in computational fluid dynamic simulation. They allow improving the quality of cells in the mesh, considering the influence of the gravity on the flow and accurately treating the boundary layer near solid walls. In addition, they define the distance between the solid surface and the first cells of the mesh, assume contact density in the simulation domain, and calculate gradients in physical properties. By dividing the following domain into discrete regions, they facilitate the solution of flow equation independently. In this part, we can observe the initial conditions where the use of Bogota pressure and negative gravity stand out. On the other hand, as for boundaries, this inlet with mass flow rate and outlet with outlet.
In order to make the simulation, we first need to make the 3D CAD model. That's why we need the following measures to make the right modeling of the 3D CAD model. So we decide to use D1 that equals 0.145, that was the inlet diameter, D2 that was the outlet diameter and the value was 0.270 meters, and the angles that we use was the inlet blade angle was 0.24 rad, and for the outlet was 0.55 radians. Finally, we choose to use 8 blades.
So now we have the mesh independence. Here we got the values of the efficiency and total health for the flow of the best efficiency. These are the results of the CFD simulation, with the three types of meshes and the values reported in the producer's curve. Here we can see with the errors in meshes that their differences are not big compared to the difference between their computed time. In this order of ideas, we selected the thick mesh because it can give good results with a less computed time. And now the following graph shows that type of behavior. Here's the graphic that confirms what was said above about the use of the thicker mesh.
For our simulations, we used the conditions showed in the presented table. We simulated flow rates for both water and oil. In effects of the comparison, we will only analyze the five flows showed in the table. It was fundamental to calculate the Reynolds number to know which flow to simulate, which we determined using the analysis reported by Ivan. As a result, we obtained a turbulent flow for both fluids. To calculate our BEP, we simulated the flow rates showed before plus some extra to get a better fit. We plotted the flow rate versus the efficiency, and in the graphs we can see the adjusted curve we obtained. The R squared of both graphs was 0.998, which suggests that the model can explain almost 100% of the variability in the observed data. By finding the maximum value of the curve, we obtained a BEP of 260 cubic meters per hour with a 3.96% error for the water, and 245 cubic meters per hour with an error of 2.04 for the oil. As we can see on the graph, all the cases present the same behavior, being the reference pump the most efficient, followed by the water, and lastly, the oil. The oil pump is less efficient due to the fact that we designed the pump modeling with water. Also, the oil is more viscous, which results in more losses and less efficiency. As we can see on the graph, in all the cases the head decreases as the flow rate increases. This occurs due to frictional losses. We can see that in both water and oil we have an increase and then a decrease around the 50 cubic meters per hour. This shows that the pump we designed might be unstable due to assumptions made during the design process.
Here we can see animation of the streamlines for the oil and water simulations. There is a difference in the velocity profile at the pump inlet, which can be explained by the differences in viscosity of the fluids. Being more viscous, the oil generates a higher shear stress with the walls of the pump inlet. In the impeller part, it is observed that in both simulations similar speeds are reached, which is related to the fact that in both the rotation speed is the same.
We can see in the velocity profiles that they do not vary significantly between the values obtained for water and oil. Additionally, it is notable that the velocity decreases near to housing. Finally, it can be said that two nothings of recirculation are observed.
In the comparison water versus oil G+, we can see that the oil has lower values than the water. This is because the viscosity of the oil is higher than the water, and that's the main reason why the G+ values are lower in the case of oil versus water.
Cavitation is the sudden formation and explosion of vapor bubbles at the points inside the pump where the absolute pressure drops below the vapor pressure of the fluid. To prevent this from happening, it is necessary to ensure that the pressure applied to the suction port is always higher than the vapor pressure. To verify in which points there was cavitation, the absolute pressurizing was carried out, and the maximum value was set as the fluid vapor pressure. From this, it is observed that for the simulation of the water, the pump cavitate at the inlet of the blades for the flow points of the manufacturer's bed, as well as calculated bed, free delivery, and medium point. In the old simulation, there is cavitation in the flow rate of the manufacturer's bed, free delivery, and medium point. Unlike water, there is no cavitation in the calculated bed.